All right, let's jump right into a seemingly impossible contradiction that is literally rewriting the rules of global infrastructure. So for well over a century, the engineering world has held on to a fundamental assumption about concrete, which, by the way, is the second most consumed material on Earth, right after water. We basically believed that to make it significantly stronger, we just had to alter its chemical recipe. Engineer better additives, invent advanced chemical mixtures, or use complex fiber reinforcements. But today in this explainer, we're going to unpack a major breakthrough that completely challenged that century-old paradigm, upending traditional material science and fundamentally reshaping how we build the modern world.
Imagine taking the world's most used building material and making it up to 80% stronger under maximum compressive pressure. Now imagine pulling that off without changing a single chemical ingredient in the mix. Same cement, same aggregate, same water. From a conventional civil engineering perspective, achieving an 80% gain in compressive strength purely through mechanical handling sounds, frankly, impossible. Yet the field data proves it actually works.
For decades, the global construction sector poured billions into inventing better chemical formulas, but a consortium of researchers across several Chinese institutions, including Tongji University and the China Building Materials Academy, they completely shifted the paradigm. They stopped asking what was in the concrete and started asking what happened to it during the wet production phase. They hypothesized that the structural limits of concrete weren't actually dictated by the chemistry of the cement, but rather by the physical mechanics of the casting process itself.
Section 1. Mechanics of compression casting.
If we zoom in to the microscopic level, we can easily see why standard concrete is inherently porous. When it's mixed and poured into a mold, water and tiny air pockets just naturally get trapped. Now, traditional practice uses vibration to shake out the large bubbles, but as that water eventually evaporates, microscopic voids are left behind. And under stress, these voids become weak points that initiate cracks. Compression cast concrete, or CCC, entirely bypasses this flaw. By mechanically pressing the wet concrete, it physically ejects these structural liabilities, creating a radically denser, highly uniform matrix that fundamentally alters the material's failure curve.
What's truly fascinating about this process is how straightforward the mechanical change really is, yet how profound the structural result becomes. Basically, you mix the standard ingredients and you pour them into a mold in a precast factory setting. But then, and this is the crucial part, you apply massive hydraulic pressure while the concrete is still in its plastic state. This immense force literally squeezes out the excess air, the water, and even the excess cement paste that the structural matrix simply doesn't need in order to bond.
To put that into a real-world engineering context, the system applies between 5 and 15 megapascals of pressure. Now, 15 megapascals is roughly equivalent to the crushing hydrostatic force you'd find at the bottom of a half-kilometer deep column of water, and that is applied directly to wet concrete. Forcing the material into this hyper-dense state pushes its compressive strength up non-linearly, which maximizes the binding efficiency of whatever cement is actually left in the mold.
Because this technique requires industrial-scale hydraulic presses, it's perfectly suited for precast infrastructure. We're talking about massive highway panels, bridge beams, and railway sleepers that are manufactured in strictly controlled factory environments before they ever arrive on the job site. For a country operating at the infrastructure scale of China, where, remember, more cement was poured in a recent 2-year window than the U.S. used in the entire 20th century, the incentive to optimize this kind of precast manufacturing is an absolute economic necessity.
Section 2. P-Core Rapid Assembly Technology.
To understand the true scale of this breakthrough, we really have to combine compression cast concrete with a radically different structural system developed by a company called Broad Group, known as the B-Core panel. Just let this fact sink in for a second. In 2025, a fully functional 10-story building in Chengdu was erected in under 30 hours. Yeah, 30 hours. And this wasn't just some temporary exhibition structure. This completely shatters our baseline assumptions about construction speed. And that speed wasn't achieved by just making workers move faster on site. It was achieved by fundamentally changing the engineering philosophy from traditional building to precision assembly. B-Core relies on structural steel panels that are designed with the precision and strength-to-weight ratio you'd normally expect to see in aircraft fuselages. It effectively replaces traditional reinforced concrete load-bearing columns and walls entirely. Every single component is engineered to interlock with minimal adjustment, and structurally speaking, when subjected to severe seismic load testing, which accurately reflects the earthquake risks of dense urban zones, these B-Core frames actually outperformed conventional reinforced concrete. It introduces a completely different risk equation.
Section 3. Multiplying sustainability and economics.
When you combine B-core panels with compression cast concrete on the exact same project, the economic and environmental benefits don't just add up sequentially, they multiply. The absolute crucial point here is that wherever a B-core steel panel replaces a conventional concrete structural element, that concrete isn't just being produced more efficiently, it isn't being produced at all. The cement, the water, the aggregate, the massive carbon emissions embedded in the calcination reaction, the transport costs, the whole shebang is entirely erased from the project's balance sheet right from the very start.
But, of course, buildings still need some concrete, right? Well, for the parts of the structure that still require it, integrating the CCC method allows builders to achieve their exact structural strength targets while drastically cutting down their cement consumption by 40% per cubic meter. Because the pressing method physically squeezes out the excess paste and achieves a higher density with less binder, you're essentially eliminating the most expensive and carbon-intensive ingredient in the mix.
And this brilliantly illustrates the macro impact on our global carbon liability. Life cycle models projected converting just 30% of the world's structural concrete to this compression cast method would eliminate roughly 850 million tons of CO2 annually. To put that into perspective, that is equivalent to the total greenhouse gas emissions of the entire industrial economy of Germany. Every car, every factory, every power plant wiped out every single year, just by changing how we handle wet concrete in a factory setting.
But the economics go even deeper than just cement savings. By reducing the material's porosity by 45%, CCC exhibits a massive drop in chloride penetration, which is what normally rusts internal rebar, as well as freeze-thaw decay. So structures that historically required major remediation at the 25-year mark can now comfortably project service lives of 40 to 50 years without needing equivalent maintenance. Plus, because these elements are pre-cured in a factory, you completely eliminate those multi-week on-site curing delays, which brings concurrent time savings to the entire project schedule.
Section 4. Rewriting global standards.
Now, we all know the concrete industry is famously conservative and generally pretty slow to adopt new practices. However, these undeniable structural and economic advantages have triggered a frantic global race to license and adopt these exact Chinese breakthroughs. And this isn't just an academic experiment isolated to one specific region. The absolute largest construction and chemical firms on Earth, everyone from LafargeHolcim in Europe to Obayashi in Japan and Hyundai Engineering in South Korea, they're all already restructuring their supply chains, initiating field trials, and integrating these systems right into their smart city pilots. They are aligning to these new specifications right now as we speak.
So why is it spreading so incredibly fast? Well, because the Chinese research consortiums didn't just lock their data in some proprietary vault. They actually published the nanomechanical data and blueprints via an open license format. But let's be real, this wasn't purely scientific generosity. By releasing the blueprints while simultaneously holding 34 international patent families on the heavy equipment and process controls, China basically positioned its own manufacturers and licensors at the inescapable center of the global equipment supply chains required to actually execute these builds.
As the world grapples with the immense carbon and cost problem of our aging infrastructure, it's clear the revolution has already arrived. The structural and economic evidence is settled. So the ultimate question for every engineer and infrastructure planner watching this explainer is simply this: will global markets write their own future building standards, or will they simply adopt the ones already embedded in the very supply chains they now depend on? It's a fascinating shift and definitely something we'll keep an eye on. Thanks for tuning into this explainer, and I'll catch you in the next one.